This talk will be about physical locks, not, in case somebody didn't realize that. Sometimes you hear like, "Ooh, I'm a cyber lock picker." What do you do? Like, "Well, I pwn firewalls." No, this is about like pieces of metal in your hand. We're going to talk about actually how locks get picked, because some people might not know about lock picking. It'll be real quick. And once you've seen how lock picking works, you'll start to understand how some manufacturers have tried to add in extra steps to make their locks more pick resistant. But this whole talk is really about stories of those extra bits of hardware still being compromised if you take the lock apart and study how it works. Some people have been able to reverse engineer the locks and say, "Oh, wait, you mean if I push on this side? Oh, damn, that sucks." So we'll tell stories like that and maybe give you some ideas if in your spare time you want to take some locks apart. You'll be the next person I can tell a story about, because it's really, really fun when you can compromise an actual physical object right in your hands. It's got a real treat to it. So as we said, I'm up here as part of both Tool, which is the open organization, but I also do represent my company sometimes for professional work. You can usually tell what role I'm in by which shirt I'm wearing at a conference. So if I have like the nice polo shirt on, I'm with my company, the core group. If you see me like this, I'm in like HackerCon mode with Tool. And Tool, as he said, is just a fully open group. Anybody who wants to be a part of Tool can meet us at any of the public events we run. We do a lot of workshops. We do a lot of lectures just for the pure pleasure of it. And if you want to learn more about us, just ask me later. So really briefly, for anyone who doesn't understand lockpicking, how many people have ever done any lockpicking? Oh, sweet. How many people have never done any lockpicking? It's about a third, maybe a little less. For the few of you who've never picked a lock, you should understand that locks come in many different shapes, padlocks, doorknobs, etc. But inside, even though the form factor is different, the actual internal mechanism is almost always the same in most locks, called pin tumbler locks. When you look right on the outside, you always can kind of see there's that plug, the round part that will turn when you operate the lock. And if you look right inside the keyway, there's sometimes a piece of a pin that you can see. Many people know that a lot of locks involve pins somewhere. But if you've never taken a lock apart, if you've never really played with one, you wouldn't realize that it's actually not just a single pin stuck in the lock. It's a pair of pins. It's called a pin stack. And this pin stack is what's holding the lock shut. When you don't have a key in the lock, the plug can't turn because the driver pin, shown in blue, is binding. If you do have the right key, however, and you push your key into the lock, it pushes on the pin stacks, making everything move just the right amount, letting everything turn. Is that pretty clear? Good. Now, it's not a single pin stack. There's a series of them. And all those different sizes of key pin, shown in red, those different sizes of pin correspond to the different cuts on the depth of the blade of the key. With my wicked animated GIF here. I have no multimedia foo whatsoever. So yeah, I mean, it's a simple concept to understand. If all of the cuts are exactly right, everything lines up, and everything can, clear, everything can turn. If so much as one of those cuts is wrong, if it's a little too high, a little too low, not going to turn, not going to turn. So a lot of people think that most lock security is based around just making more pin stacks in the lock. Let's make the key longer. It's like a password, right? Like, just give more characters. It'll be harder to brute force it. Well, you don't really brute force locks. That doesn't really result in better security. That's because of how picking is actually performed. Picking relies on imperfections in the lock. A lock in the perfect world, imagine the plug has been stripped out and you're looking at it. All of these chambers would be exactly aligned. All of the pins would be exactly the same shape. And if you try to turn the plug, all those pins would bind everywhere. In that case, it would be like a password, right? Like you put the whole password in, the whole string gets hashed all at once, and it either works or it doesn't. It's either matched or not. But in the real world, manufacturing of locks can get pretty ugly. Most locks have imperfection in them. See, this is actually a brand new lock. This is not wear and tear. This is a lock that came from the factory really ugly. And the pins, too, when the pins are manufactured, they have all these pits and scarring. Just many companies don't put enough effort into the design of their lock. And because of all these imperfections, there's actually misalignment and jamming that occurs inside the plug, inside with the pins. When you try to put pressure on the lock, it's not binding everywhere. Only one pin stack, sort of the most misaligned pin stack, is the one that's binding. And because of that, unlike a password, you can attack the locks one pin stack at a time. Those of you who've done picking know this. How if you put a little pressure on the plug, you push and a pin will actually click. It'll set into position. And you can do that one at a time, at a time, at a time. You can do it all individually because of those imperfections. So that's how most lockpicking works. As we like to joke about it in Tool, lockpicking works like password cracking in the movies, where you can have like all the password numbers going, and then like an A appears over here, and then like a 6 appears over here, and then the missiles launch and stuff. But yeah, I mean, so it's one thing at a time. Push, 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 click, click, click. And it's all because of those basic imperfections. It's because you have each piece of the puzzle acting independently from one another, and you can try to attack them independently. And this is what most manufacturers of better locks try to prevent. They try to address this problem. The idea of, well, here's a piece that's putting pressure here, here's a piece that's putting pressure here. They try to take this actual binding force and make it one step removed or 2 steps removed from the actual pressure that's being applied to the lock. Well, how can they do that sort of thing? Take, for example, a manufacturer of a better lock. That's a real interesting lock. It's a company called Multilock. The Multilock design is actually, it's still a pin tumbler design. It's still the same idea. But notice there's a lot more complication here. What's actually happening is you have pins within pins. So you actually have some pins are like telescoping inside of another set of pins. So that you know how it's binding and there's pressure certain places. You can't really tell if there's pressure inside or on the outside. You can't tell which part of the shaft is causing that binding and where to find it. And it's not only that, it's of course it's a flat key. It's called a dimple keyway. It's very hard to get picks in there. It's a really, really neat idea. And this is an older design. The newer multi-locks are even more intense. But when this one first came out, this generation, everyone looked at it and they said, wow, that's really amazing. Let's use these in prisons and stuff. And where I come from, these are very popular in prisons, even this old version. There's a slight problem, however, though. And it didn't take long for some researchers to figure this out. One of my friends in Tool was one of the first people to publish this. Because you think about it, you hear the marketing material, and you look at this diagram from Multilock itself, and you say, wow, that sure does look neat. And this is what you picture. In your mind, you say, okay, well, it's got these pins, and there's kind of pins going through them inside. It's kind of like this. Boy, that sure is neat. But then someone said, well, I took this apart, and it's actually this. You say, well, wait, what happened there? It looks very similar. Is that what I was thinking of? Well, no, not exactly. It may not have been what you were thinking of. This is what most people picture. This is what's actually happening. The upper piece, the driver pins, they're not two independent systems. They're actually captive inside one another. And when you actually take the hardware apart and inspect it, you realize that there's some very strange interactions that take place. So yeah, the key pins, they can completely come apart. This can never come apart. It can move. There's actually a spring inside of the driver up here. But because it's all stuck together, interesting things happen. Now, normally the lock would operate just like this. You have dimples in the key, some of which have little bumps in the middle of them, so the pins will all push. There would never be a key with a dimple and a really big spike sticking through the middle of it. I mean, it couldn't get in the keyway, first of all. It doesn't mean you can't stick something in there, like a long piece of wire, to push really high. And look what happens. Because the top system is all captive together, pushing on the inside pin lifts the entire top stack completely out of the plug. And one of my friends came up with an attack where it kind of looks like a long comb, where you reach in, you jam, and then you can flip the plug right away. And it takes so this wonderful design is its own flaw. And it's immediately obvious if you just take you guys know this a lot. If you just unpack a binary, if you actually look at it, you're like, oh my God, this, it just jumps right out at you. This is a perfect example of that. A really cool system that sounds awesome and looks awesome in a marketing brochure. But when you take it apart, the first thing you see, you're like, whoa, this should not be like this. And sure enough, Multilock first, they're like, oh, no, that doesn't really work that way. And then they eventually changed their design. Their newer locks are really, really gorgeous. There's still plenty of these out there, plenty of them in prisons. I don't know if I trust them like that, but so there you go. There's one simple story. Many manufacturers have tried to address the problem of picking, however, not by changing the pins themselves up here, but by augmenting the pins with what's called a sidebar. And this is what I meant when I said trying to get that mechanism of release one step removed or even 2 steps removed from the pressure someone's putting on the lock. So normally, if you put pressure on the lock, here you have, the pins would just bind directly. The idea of a sidebar is to get the pins to bind not directly into the pressure you're applying, but so the pressure applies force to a sidebar, that then applies pressure to other sets of pins. So it's, again, just trying to step back, step back, step back. So your direct pressure can't be manipulated and felt by hand. But that same idea, the idea of small imperfections, things that don't all touch at the exact same moment, that sort of problem can be encountered with most sidebar locks. The idea is, if you can figure out where they're interacting and how the pieces interact, you can still get something to fall into place first and then something else to kind of fall into place a little bit later. You can divide the lock up into sections and try to just put pressure here, then put pressure here. Let's look at a very popular sidebar lock. This is, a typical sidebar lock called a twin lock, where there's main pins and then there's side pins being interacted, and just the sidebar itself has fingers that stab into the sidebar pins. In Europe, the ASA series, the twin series as they're called, are very popular. Here in the North American region, the Schlage company actually makes a lock called the Primus. The same idea. It's a series of additional pins that have to lift and even twist slightly into position to interact with their sidebar, and that's in conjunction with normal series of pin stacks. I don't know how much here in Canada, do you encounter Medico locks? Some yeses, I see them, yeah, some Fed. Yeah, where we come from, the US, the government loves Medico locks. So Medico is also a sidebar type system. It's a really pretty cool one in the sense of how the sidebar interacts. It doesn't need a separate series of side pins. The regular pin stack is all it needs because the pin itself on a Medico actually spins into position. If you've never seen this, it's a neat idea. It's a concept they've been working with, the same concept for quite a while. Excuse me. But the notion is to just get the pins themselves to turn. Now, how do they do that? Well, they do that by having actual chisel sort of tips on the front ends of the pins. And the cuts on the blade of the key, I don't know if you can see that. The cuts are actually at odd angles. So when the key goes in, the pins are riding across it and they're actually rotating into position. We can try to look at a little video I shot of a Medico lock I pulled apart, and you'll see what I mean. So right here, this is the sidebar that would normally be inside of the plug. It would be up against in a slot. And all of these little black dots, dot, 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 those are the grooves on the side of each pin that would normally accept these teeth. So watch, when the key is actually removed, flip, 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 kind of randomizes all of them. When you put it back in, flip, 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 and at the last moment, they're all in the right alignment. Really, really neat concept. Now, the problem is, in order to get this to execute the way you want it to, anybody who's worked with mechanical systems knows there has to be a little bit of flexibility, a little bit of room for error. It's not like, writing code where you're going to return a 1 or a 0. It's going to be some sort of mechanical, metal object, a key that's been in someone's pocket for a while. We can look at it from the side, too. So if someone's key is a little bit worn down or a little bit, rubbed off or just manufactured a little bit poorly, there's no way that down to a perfect micron level, a piece of metal is going to go in a perfectly flat slot. You have to have some means for the user to interact with their lock. There's the sidebar. Some means for them to interact with their lock that's a little bit forgiving. So imagine we're looking down from above on those pins that rotate. Imagine a slot like this. A perfectly exactly aligned, hello. Oh, come on now. Really? All right. That's all right. Is my Wi-Fi on? Who just did that to me? That's all right. We were running a little fast because I talked too fast. So that was just life slowing us down. There we go. Let's see if it'll work now. Yeah. So imagine, in a perfect world, which clearly we're not in, but in a perfect world, you could have a lock like this. But obviously, in the real world, that doesn't work. You could never reliably expect a lock to just snap into position exactly every time. And Medico knows this. And as they've designed their locks, they actually have slots on the side of the pins that are a little bit angled. The channel's a little bit not dead even. So it gives you some room for movement. And that makes sense, of course, in a mechanical world. But because of this, because there's a little bit of flexibility in how the sidebar can line up, it means the sidebar can grab into those pins not all at the exact same moment. It means that if the pins are a little bit uneven at any time, the sidebar still has a chance of getting in ever so slightly. The fact that the sidebar can sort of dig into those pins, if you put pressure on the plug, it's going to try to stick the sidebar in. If you can get those pins moving, if you can get them to start turning, you can actually start to catch a little bit, and the fingers will nestle into those slots. So someone named Mark Tobias, also a member of Tool, also noted in the lock research community, he wrote a book with his partner, Tobias Busmanis, all about the Medico lock and how he's basically done mathematical algorithm on all the different possible positions that these pins can be in, because they're not infinite. The Medico design only has, a few different angles of pin operation. And he's made a special key. First it was a series of keys. It was like 16 keys. Then he did it, all right, well, if one of these pins is passing by another one, I don't need all these extra. I can get this down to like 4 keys. And now, even reduced from 4, if you're lucky, you can insert a couple Medico keys, specially prepared keys, that will quickly flip all the pins one way and then the other way, trying to grab the sidebar. You can completely take the Medico sidebar out of the picture. Come on. There we go. So here's Mark talking about, he's actually going to demonstrate a bumping attack. I'll talk instead of him. This is his magic key that has a series of cuts, and he's putting pressure on the lock as he inserted that key. So he snapped it one way, hopefully getting all of the sidebar to just catch all at one moment. And he says, all right, he's blah, blah, blah. He's talking about, he hates Medico. He's like their number one enemy. He just sits there griping about this company all the time, to the point where he's almost a little obnoxious. But he's done you can't argue with results. So he has the right to speak like this, in my opinion. Takes him a couple of attempts. He goes tap, tap, tap. And he bumps a Medico lock completely open, a government-grade Medico lock. This has become so amazing now. I wonder if my laptop speakers will be able to hear this. You can actually, it's amazing to hear a bunch of people, competitive lock pickers, trying this technique. Tell me if you can hear my laptop here. No. You know what? Let's use this microphone real fast, because I really want you to hear. This is a lock-picking competition that took place in Germany. Is this microphone hot? Can you hear that at all? No? No volume? You can't hear it? So did you hear that? Snap, snap, snap. The keys were going in and out. People were just setting all of these locks, setting all the pins with keys. Then they switched to their picks. Again, Medico lock, bang. All because they could take the sidebar completely out of the equation with the right series of keys. And that was only possible because people just took the lock apart, looked at it, and said, wow, all right, I see not only how it works, but I think I see how you can make this thing not work properly, like at all. Now, perhaps my favorite, because it was my friends and I who really loved to demo this, a buddy of mine named Shane, who talks about the Quickset Smart Series. The Smart Series is a real interesting lock, and one of my favorite stories ever about breaking of reverse engineering of locks. I brought one of these to the REcon conference in Cleveland one year. And I said, hey, who wants to try to pick this? And I just saw it was this new thing that had come out. It looked cool, and it looked expensive. So I said, all right, maybe this will be an interesting lock. And nobody could pick it at REcon. I was like, oh, wow, maybe this is a really good lock. Let's take it home and let's see how this thing works. It wasn't till I actually got the thing home and took it apart. I said, oh, wow, that's kind of weird. Why is it like that? And I called a few people and I said, is this thing supposed to work this way? They said, yeah, that's just how they make it. And Shane, completely separate from me, he bought one because he saw it at the conference. He said, man, I'm going to go buy one. And he took it, and he also said, oh man, that's really cool, but that's probably bad. What made us all think this? Why was our reaction, hey, that's cool, and hey, this is bad? Well, first of all, it has to do with, hey, that's cool, with how pick resistant this lock is. Notice this is a sidebar-based lock. The sidebar interacts with a series of sliders that have all kind of false notches. So if you try to put pressure on this lock and try to push against the pins to make these sliders move, you'll jam on all these false notches. It's very hard to pick this lock. Only when the exact correct key is put in does everything lift, does everything turn, everything work nice and even. The problem has to do primarily with this lock's, quote, re-keying function. So here is what's called, the SmartKit re-key kit. Now this is not an amazing kit. This is only the original key to the lock, a different key that you could use if you don't need the key from this thing, you can just buy another key, and this in the middle, which looks all, ooh, what is in this little red piece of plastic? It's just something about the size of a toothpick. Here's what happens with, quote, the re-keying function of this lock. If you have the lock open, so right in this moment, the lock is turned and it's open, you can stick essentially a toothpick into the lock, knocking all of these sliders, because there's one for every pin, it knocks the entire grid of sliders off of the pins. So these teeth and this pin become separated, and they can move independently. With those sliders all knocked off, you take the old key out, you put your new key in, so it changes the height, it changes the position of all these, and then when you pull the toothpick out, they marry back together, and now they're at a different series of heights. So instead of being, let's say, down here, the slider could be attached at a completely different height, thus operating at a different keying bit. So each pin stack can be set to a number of different positions. It's a neat idea. I think it's kind of cool, and the fact that they did it, making it hard to pick, that's kind of respectable. The problem, in our opinion, is how badly they actually implemented this mechanism. So if you have one of these pins attached anywhere, at a high position or low position, or anything in between, it doesn't matter. If you push the pin all the way up to the top, like by reaching in with picks, or by taking a blank key, a key that has no cuts, and just sticking a whole blank key in the lock, it'll push all the pins way up. This right here, and you'll see better pictures in a minute, this is not a solid wall, because this little bit of red, can you see that the red tip? That needs room to move. It needs to be able to traverse this whole slot. So if this whole slot is open, there's nothing in there, with this pushed all the way up, you can stick anything, really, into this lock and feel all of these little bumps. And they're the same wafers in every lock. There's only 6 slots. And if you can reach in there and feel how many slots there are, you can't pick the lock, but you can decode it in like 3 minutes. And you just write down a few numbers, and then you can go to a locksmith and make a key. It is the coolest trick, in my opinion, because Shane did this for about $4. He took a blank key. He said if he already owned a Dremel tool. If you don't own a Dremel tool, go on Craigslist, and then it costs you like $12 to do this attack. He took a blank key, cut a big notch in it, then used a needle, a little piece of metal. This is actually from an anti-theft tag, inside of CDs or DVDs. You get those pieces we use those all the time to slip into locks and to pop them open. But he used a little piece of shim metal, some glue, and something on the end of his pin, and he made this. Does everyone see what he did there? This blank key will go in, it'll lift everything all the way up, and then this long channel on the side will accept this flag. The flag normally sits in here, and you can just go in one step at a time, just turning the tool, and the flag will rub along and actually touch every one of those little notches, and you can just count them. So just because the lock is not pickable, yes, it's very hard to pick this lock. It doesn't mean the lock isn't leaking information everywhere. And, he said it's great that, this is this wonderful anti-pick lock, but he's like, please, no one thought of this? He did this in no time at all. And now this, quote, amazing lock, I wouldn't trust this at all in any sort of high security application. Even though, yes, it's hard to pick, here's another view of that channel. This little bit is like that red tip. So this whole channel is open and exposed when you lift it all the way up. You're just reaching right through. So yeah, it's a neat design in one way, but no one at all thought, they said, all right, well, we're just going to protect this against lock pickers. No one thought about people reversing the lock. No one thought about, hey, what if someone just takes this apart? What kind of information is this going to reveal? This is possibly my favorite quote ever from Shane. This is Valenex giving his talk at ShmooCon when someone asked him the question about disclosure. As many of you probably when you do some RE work, you're encountered, well, how do I tell people about this? How do I notify people about this? And it can be frustrating when a company just shows no interest in security. When you try to get in touch with them and they just don't respond. Again, I hope this microphone picks this up because we definitely want this quote, which is possibly the funniest thing I've ever heard in the lockpicking world in maybe 3 years.
Has QuickSet had any response to my findings?
Can we hear that? Let me check my volume over here. Yeah, that's up. Let me just pop it up way up over here. Sorry, I didn't ask them for a audio feed. I should have just done that.
Has QuickSet had any response to my findings? No. I didn't notify QuickSet about my findings. If QuickSet couldn't see this coming, then, that's their problem. This isn't rocket science, people. I'm not writing code. I super glued a little flag on the end of a needle. And I stuck it in a hole, and I said, oh, look, wow, it's great that you sell these things for $100, but it sucks. So, yeah, they don't know. They will, I'm sure. Someone will tell them now. I did talk to Skylar, and I asked him to get a hold of his contact. His contact never called him back. So.
Yeah, I love that quote. They will. Someone will tell them now, I'm sure. But, that's the problem we all face. What do you do when, how do you guys handle it? Do you kind of give them like a company a month or two to get back to you? And we try to always encourage responsible disclosure, but that's a real important ethical question. And I always ask people about, and I'd love to, pull me aside later. I'd love to hear how you do it more in your own work. The idea of when does responsibility shift from sitting there silently, waiting for a company to get back to you, versus the public's interest in hearing about an important flaw. It gets a lot harder for us in the lockpicking world because if you guys publish something, like the company doesn't get back to you at all, they just don't respond, and then you publish a proof of concept, you're not giving away a free exploit, and they say, oh yeah, shoot, this is bad, and then they rush a patch. They can just put that and say, all right, everyone download this patch because this person over here found something, and now we got you covered. Well, we don't have that same luxury. A lot of times, companies will come to us and they say, they will respond. They'll say, oh yeah, you've really found something here. We're going to get right on it. And to a lock company, like get right on it means maybe in like a year, they'll have something because they have to retool an entire factory. And then on top of that, it's not like all the customers that are out there can say, oh, I read about this problem. Let me download the new lock. Like, no, it's millions of dollars, and people have to roll out these fixes slowly across whole facilities. So it definitely makes me feel awkward whenever we encounter something like this and how you approach a company and what's a really appropriate timeline. I'd really love to hear stories of what you faced, and I'd love to hear what you think from an outsider's perspective. what you think a responsible disclosure should look like in the physical world. How do we find that balance? It's something I'm always thinking about, and I'd like to know more about from you, because I really respect your opinions there. There's one other thing about the Smart Series that I should point out, just because, again, it's really funny. So this whole side of the plug, because of the rekeying mechanism and because it shifts around and it's multiple pieces, for the longest time, and still in some pieces of most of these locks, almost that whole side of the plug is plastic. It's not metal. Because they have to have all these little extra cuts, the way they make it. It just was manufactured. It made sense to manufacture it in an easily workable medium. Okay, I understand, but apparently, again, no one thought when someone said, hey, what if someone takes this apart and looks at it? Are they going to realize this is really cheap, material? This is not strong material? Well, some of us did. A few of us started, saying, hey, I wonder, blah, blah, blah. Do you think you could crush this? Do you think you could push this? And somebody talked to a company in California who made this tool, which I just call the smasher tool. And then when I said, oh, man, that you guys really did design it very well. I'm going to make a little video about this. So this is not elegant at all. But I find it really humorous. And since I'm talking about the quickset lock and I had a couple extra minutes, I wanted to include this anyway. Just, again, the notion of expect people to take stuff apart and either A, try to finesse a solution, or as you guys know, in the freaking digital world, if someone looks at your code and is like, oh, I bet I could fuzz the hell out of this, expect people just to throw everything they've got at a vulnerable line of code, a vulnerable input or a buffer. This is essentially the biggest brute force attack ever. But it's only possible because someone took the lock apart and said, hey, plastic, that doesn't belong in a lock. This is what I call the quickset smasher tool. I'm going to pop the volume up again some more on this.
Quickset Smart Series before knows that this lock is pretty overrated. There's easy ways to decode it. It's overpriced for the manufacturing processes involved, but never until I actually tried this particular tool did I realize what a complete waste this lock is. So here we have Smart Series doorknob, and it is locked. Now anyone who's taken these apart, or has seen them taken apart in one of Shane's talks, knows that there's a whole lot of plastic involved in one side of the plug. The entire rekeying mechanism, in fact, is mostly plastic components. Well, I guess it should come as no shock that someone designed a tool basically just to smash the hell out of the insides. Now, I've been fascinated by the fact that while this is a really destructive attack, it actually isn't all that obvious from the outside. So here we put our quickset smasher tool in the lock, and not even mounting it in this door. Now, this is a fresh doorknob, and I don't like doing this because it takes, $50 out of my pocket each time. But here we have our locked doorknob. Now, just holding it in my hands, I can still take this tool. I don't know if we can hear this. And just crunch all the plastic. Now, this doorknob's open. I'll pull it back out. Not only does it work fine, it looks fine. And if that's not crazy enough, come along later, put the tool back in.
Yeah.
Tomorrow to Datagram. You can do some
Yeah, I mean, I mentioned how it's really bad for the inside, obviously. And we have one of our team at the core group does forensics, and he took some photos of it. But yeah, it's still that's freaky, man. So yeah, it's really fun finding all these different attacks, finding all these different things. As you guys know, if you just take something apart and you look into it, you're like, hey, how do these pieces fit together? You never know what's going to jump right out at you. And all of my friends and I, we get a real kick out of this, not just picking the locks, but breaking the locks, and hopefully making the locks, even better. Because that's what all this is about. I don't have to explain this in a room of people like you guys. You talk to some feds or something, and Sometimes they get it, and sometimes they don't. A lot of people say, why do you do this crazy research? Are you just trying to break things to make them worse? Well, no. We're trying to break things to make them better. That's the point. That's why you're all here. That's why I do this. That's why we do what we do. And I get a real big kick seeing whole roomfuls of people that just get it, because it makes better security for the rest of us. The newest Quickset, the newest generation, has more metal in it. It's a lot harder to do that attack, the smash attack especially. We have another video that I didn't show because it doesn't look as cool, of a buddy of mine, Dr. Tran. We're like, all right, let's try that Quickset attack again. And bang, and he just smashes the whole tool off and jams it in the lock. Because, they've hardened it. It's still possible in some ways. We've done it a couple times, but not reliably. The multi-lock, I said the newest multi-lock, it's a lot harder to pick. Yes, it's a really good design. The same principle is used all the time whenever you're trying to reverse, well, anything really. You just split it up into sections. You try to divide it up and say, well, these pieces interact with this, and these pieces interact with this, and it's supposed to all happen at once, but I wonder if I can stick something in there to kind of interfere with that process. Can I just make this thing do something, and then can I fuck with this? And then all right, now I can come and deal with this. That's the idea. If you want to get into this, just don't think of the lock as one whole big insurmountable mechanism. Say, all right, well, I see how all these things work. Can I get them to separate? Can I get one piece to touch one side and ignore the rest? Dividing your workload and then conquering each little bit separately, it's the same thing you do all the time. And yeah, it's really, really possible. There are a few brands of lock that I always mention in my talks as, quote, locks that I love. I mention them now because they are locks that maybe I will suggest if you want to get into this, maybe you try to bang your head into one of these. The Abloy system from Finland is the actual Abloy ProTech. It's a beautiful rotating disc design. It's a sidebar-based lock, but it has no pins at all. The sidebar interacts with a series of wheels. They're little discs. They operate like the wheels inside of a safe. It's like a miniature safe. It's a really neat design. I have my keys if you want to see my Abloy keys later. The EVA company from Austria has the magnetic code system. This is a lock that has magnetic elements in the lock, which that's not too rare. A lot of Japanese locks from Miwa have magnets. But what's really unique about the EVA is that it's not just little north-south magnets, because some people have worked on trying to reverse engineer Miwas with little microcircuitry, and they're just trying to read the magnets off a little reader head. The EVA actually has north and south in discrete zones on the side of the key, so discs that are rotated north and south into different positions. When you stick it in the lock, little wheels inside the lock actually spin. So the idea of trying to reverse that lock, how do we get in there? How do we make those wheels spin? Can you use small magnetic motors? There's a million fascinating questions that you could talk about, and I can show you some diagrams of them if you want to play with them. And of course, the newest multi-lock, the MT5, their newest generation involves not just their basic pins, but also a series of what are called sliders with a long groove. It's considered to be one of the most secure locks, so I'm glad that they rolled out a new design. It's only that secure because people keep attacking these things and trying to push multi-lock to get better. Multi-lock's actually now part of the ASSA ABLOY group. ASSA ABLOY has bought up all these manufacturers now. Like Medico is owned by ASSA ABLOY. EVA is still their own company. But yeah, these are probably three of the nicest locks. If you're really interested and you really want to do a lot for the lock community in an open source kind of way, I would also encourage you to look up either Stanton Concepts or just Google RKS, the robotic key system. The RKS lock is a purely, quote, basically call it an open source lock. John Stanton just had this idea. He's like, I got a pretty neat idea. It's sort of a rotating design mechanism, but he publishes all his specs, and he comes to tool meetings, and he comes to Fool meetings and LI meetings and all these sport picking groups, and he goes to academic campuses, and he's like, here's what I did. Break it. Make it better the next time, and he'll make it better the next time. And he just takes input from everyone. And it's so cool to see an actual manufacturer not running away from researchers, not being scared of lock research, but instead to actually embrace this kind of community, to embrace the hacker world, the researcher world, the exploit labs, and every other person. He's saying, I love what you guys do. Try to do it to my stuff, and then tell me how you did it. And so now the RKS lock is bloody brilliant. It's probably going to get contracted out for a lot of shipping container use and a lot of customs department use. And I'm very proud of him. He deserves that because the way he approaches security. So, way to go, Stanton. We will do the workshop, as we said. We will talk just about, in this workshop, field stripping of locks. You may have picked, I saw a lot of hands when you said, yes, we've picked locks before, but if you want to actually strip a lock apart, I brought a whole bunch of equally sized, equally shaped locks, and they're easy to take apart. We will just have fun with that so that it'll give you a grounding, if you want, in taking apart higher security locks. The idea of how do you take one lock apart, put it back together, it could be fun. We'll sit there at lunch, trade stories with me. Again, I want to hear your opinions about responsible disclosure and how that's affected you. I love those kind of stories. And I hope you like these kind of stories too, because I was really entertained by talking about them, and I was really, really happy to be here today. This was a real treat for me. So thank you very, very much.